And it's smelly. Why do we put lemon on fish? Other than the taste, what was one of the original reasons?
To mask the taste.
I'm assuming because it's acidic.
Because it's acidic, and what will amines are basic. What will the acid do to the amine?
Neutralize the nasty.
The what?
Neutralize the nasty smell.
Okay, you can use the term neutralize. It will convert it. The acid will convert it to the salt form, ion. So is this going to be more volatile or less volatile? IMFs. Which has more IMFs? Anybody else?
I'm trying to think, so the NH2.
We covered this on Friday, right, last week?
I guess it's going to have less branching on the NH2, and so maybe it'll be.
Yeah, but branching is van der Waals. It's very weak. I would start with the stronger
Hydrogen bonding.
IMFs. They both have hydrogen bonding. What's the difference? We look for the difference. What's the difference?
There's more hydrogen bonding on the one on the right compared to
That's number 3. What was number 4? Somebody have the 1 through 4? Ion. We ranked them in order.
Dipole.
Strongest. We said just start with the strongest. What's the difference? Potentially more hydrogen bonding, but now it's an ion. That's the greatest of the IMFs. Much more IMFs between the molecule. What's that going to do to the boiling point? Increase it. What will that do to the volatility?
Decrease it.
Decrease it. Okay. Application of the material there. Okay, let's see where we left off then. Actually, before we do that, again, good morning to everybody. We are underway here. How are we doing on IR? Any questions about IR? Question?
Okay, so most of the time, because there's multiple things that could be on one, I guess, what is it?
Spectrum?
No, I know. one
Position
spectrum.
of the
Yeah, one
spectrum?
position of the spectrum. So is it, because I noticed that you said the first day that is not more of how broad or how,
Intense?
yeah, how intense it is, just rather that it's there or not. So how, like, how we differentiate between if there's two things that can be on that one spot? Is there one that's just always that we would assume that that's it at this level of?
What are two things? Think about your question. Let's look at what two things you're talking about. Keep in mind, you need to be able to work the problems that are in the workbook. Is this keeping you from successfully working problems in the workbook?
Yeah.
Okay, then show me the one that, the exact one.
Okay, I can do
Yeah, let's look at it. Other questions? Good. Other questions about IR? Questions about lab, last week or this week? Your formal lab report's due when you come to lab, either Thursday or Friday. Solubility lab. Questions about that? Questions about lab, this question?
For lab last week, when we had to do the acid base, do you want us to show those calculations when we do the lab, or? Because it was supposed to be like an approximate, but we like sorted it on the calculation or figured out, we want to show how we did it, or
If
just
you
write
think
it
that
out.
will make a better report, then show it. If not, it's up to you. Other questions? Questions about lab this week? This week you'll be getting two unknowns, one liquid, one solid. Your mission, if you choose to accept it, is to identify them both. You will need to run IR. You'll also do distillation of your liquid and, well, among other things. There's a video about the distillation technique on the YouTube page of me demoing distillation. Questions about anything else? DQ page. Question?
Number 3.
Cipro had the wrong structure there. You corrected the structure.
Sorry?
Number 3, the structure of Cipro is incorrect. You corrected it. As I mentioned in class, the structure there is incorrect. The correct structure is drawn below or on the flip side. So number 3, the structure is incorrect. Seems like you need to look at it again. Okay, let's look at physical properties. I think we're about done with that. Any questions there? Warm-up questions? First page, second page. Any questions about those warm-up questions? Have we do on the back side of the warm-up page? First page. How did we do? Questions about the warm-up page, physical properties warm-up page? Yes?
1,4-dichlorobenzene,
Uh-huh.
the two chlorides, those kind of cancel each other out a little bit on that molecule?
Yes.
Where it's got a more polarity than vitamin A, but not obviously because of hydrogen bonding, but see, not.
Well, 1,4-dichlorobenzene is very symmetrical, and you can envision dipoles canceling out. And is that a polar molecule? Vitamin A polar?
It's got a big old tail, non-polar tail, only there on that hydrogen bonding area.
Yeah, but the question was not which is more polar. I mean, something else to answer the question? Ultimately, that's probably the answer, which is more polar, but also, I mean, what else could you be looking at there?
I mean, I think it's Tylenol because of the hydrogen bonding and the electronegativity on the other end.
Yeah, but you were comparing 1 and 3.
Okay.
Question, yeah, okay. Question doesn't ask you to compare 1 and 3, but
I mean, I would say vitamin A is more soluble in water than dichlorobenzene.
it might be tough. It might be a close call. But then I see the question was not to rank those two.
Yeah.
Sometimes a question there may be an answer, but then
A better answer.
1 and 3 is hard to tell, because 1 and 3 were neither one of them was the answer. Number 2 was the answer, right? How we do on those?
Can you go over number 7?
Question.
Number 7? We haven't quite got there yet in class. We'll talk about extractions a little bit. We'll mention that briefly right now, and then we'll see it more in acid base. Okay. Okay, guys, let's finish up the physical properties handout. Where did we leave off at? Solubility. We looked at some solvents. Those are some very common ones. Common organic solvents. What about water? Is it good for anything? Inorganic salts, sodium chloride, potassium phosphate, yeah. What about organics? Some neutral organics are soluble in water, more so in hot water. In general, though, our opening statement is organics prefer an organic solvent over water. Right? Water's not organic. Or an organic would prefer an organic solvent, like dissolves like. Organic salts, though, are more soluble in water, like methylamine hydrochloride. You can make it something ionic. And that's our opening statement. If you can make it ionic, then the organic will typically dissolve in water. We can make something ionic using acid-base chemistry. You did plenty of this in Gen Chem, especially Gen Chem 2, right? Are all organic salts soluble in water? Is our opening statement applied to everything, or is there exceptions?
Exceptions.
Always exceptions to everything. Here's some organic salts that are not soluble in water. Calcium oxalate. It's actually a dianide. It's organic though. It's got carbon. Calcium oxalate. Not that soluble in water. That's why in the body, which is largely water-based, right? Unless you're an alien from the land of acetone or something. It forms kidney stones because it precipitates, even though there's lots of water around. It doesn't stay soluble. Gout. This molecule here is sodium urate. Salt. It's organic salt. Not that soluble in water, so it precipitates in the joints, etc. So not all salts are soluble in water. There's some text there about salts. For solvents, water, etc. I'm not going to read that to you. Extractions. We'll talk more about when we move on to acid-base chemistry. Extractions are very useful in separating compounds. Acid-base extraction, we try to do some acid-base chemistry to separate compounds. These two. The carboxylic acid is much more acidic than the alcohol. If we have a mixture of these two, we can dissolve them in an organic solvent such as dichloromethane. They'll both dissolve. They're both neutral organics. They dissolve in the organic solvent. But if we add in some sodium hydroxide solution, first off we get two layers because the aqueous solution doesn't mix with dichloromethane. Two layers in our separatory funnel. If we shake this up, chemistry will actually take place between the sodium hydroxide and the carboxylic acid. It will deprotonate it and make it an ion. It will not deprotonate the alcohol. The alcohol is not acidic enough. pK about 16. Not acidic enough, right? pK of a carboxylic acid, we're about like 4. So this will be converted to the ion. This will stay neutral. Ion or organic ion will prefer the water. Neutral organic will prefer this. Now we have them separated into two different layers. We can just drain one layer into one flask, put another layer into another flask. We have separated the two. Two different flasks. If you want to get back maybe your alcohol, you just boil off the solvent, and you'll be left with the alcohol in your flask. This one, you can boil off the water, you'll be left with the salt in the flask, but instead you might want to regenerate the original. You can treat this with acid and take it from basic to acidic, and if your original is a solid, it may precipitate once it becomes acidic and once it reprotonates. It may not, depends on, but theoretically it could. And if it precipitates, then maybe you could then filter it off and you could have your original compound isolated that way, and you wouldn't have to evaporate the water. Separating compounds by acid-base by getting one of them to become an ion where the other stays neutral. Does that scenario make sense? Questions about acid-base extraction? We'll see it again at the end of the next handout. A couple of miscellaneous things. There's the molecule there is Crestor. Lowers cholesterol by inhibiting the HMG-CoA reductase enzyme. It binds to this enzyme. How does it bind to the enzyme? How does any molecule interact with another? It interacts by IMFs. And you know 4 major types of IMFs, right? What's one type? Van der Waals, which is basically what portion of the molecule or what features of the molecule would do van der Waals?
Single bond? Sigma bond? Single bond?
Nonpolar hydrocarbons, yes. They're actually illustrating that here. The compound interacting with the enzyme, how? They're showing some van der Waals attractions between these hydrocarbon groups here, small. Some type of non-covalent interaction with these amino acids. And if you look at these amino acids here, if you know your amino acids, all of these have sort of alkyl hydrocarbon side chains. So the side chain here is interacting here by van der Waals. They're calling hydrophobic bonds. First off, it ain't a bond, it's a non-covalent, so it's bond. It's like hydrogen bond is not a covalent bond. What does hydrophobic mean? Water hating. You know, that's just alkyl group, water hating. You got these water hating alkyl groups interacting with each other by van der Waals attractions. That's pretty weak, what they're illustrating. Or there's some stronger IMFs. Here's a pretty strong one. The anion of this carboxylate is interacting with the ammonium group. You could envision that being hydrogen bonding, but it's also ion pair interaction. It's number 4, right? Ions, ionic attractions. You got to be careful about some of this. For example, why do they have the O kind of connected to the O? Or it's like it's in. I mean, this is supposed to be hydrogen bonding, but whoever drew this was either didn't know what they were doing or they were half asleep. That is not a good detailed representation of hydrogen bonding, right? The O interacting with the O. One acceptor interacting with an acceptor. I mean, no. The H interacting with the H. They just were too lazy to draw the H like this and have the lone pair interacting with the H. You gotta be careful. Everybody ever see this sort of issues with this? They even have an F hydrogen bonding with an H. Can that happen? The H is on an N, so that's a good donor. Can an F be an acceptor? Okay. Well, look through there, see if you see any other problems. I mean, somebody needs to go back to organic chemistry number 1 there. Crestor. Okay, there's some other things down there. Soap. Typical soap. Anybody take a bath this morning? Good. Typical soap has a long hydrophobic portion. Then it also has, the molecule has sort of this polar head group. It's got dual character. This helps the soap interact with water. And this helps the soap interact with what?
Oil.
The oils on your skin. And so it brings the oils and the water together and it helps. It's kind of like an arbitrator. Oil, water, let me help you mix together. And, okay? you look on the back of your shampoo, you'll see something like sodium palmitate. It's some long-chain fatty acid. Hydrocarbons, a portion, non-polar, hydrophobic, often called fatty. And then you got the acid portion in the ion form. Put an H on that, that's a carboxylic acid, right? Okay, it's the salt of a carboxylic acid. It can also interact with the grease molecule. The hydrophobic portions can interact with the grease, leaving around here the polar portions which can interact with the water. And so this is sort of like a micelle. Anatomy of a soap. Lots of applications here. Sometimes I'll spend time on these, sometimes I'll just push through. I would hope that you would look at these and say, what have we talked about that is being applied here? Here are 2 drugs to treat heartburn, acid reflux. Prilosec and Nexium. Ever heard of these? You ever watched TV? What's the difference in the 2?
Next one looks better.
The difference is this one is protonated, it's got the H on it, it's neutral. This one is an anion, nitrogen anion. How many lone pairs on that nitrogen? Yes, 2. They haven't shown the lone pair in the whole molecule. If you got a minus, you got to have a plus. What's the plus? Magnesium, but that's 2 plus. That means for every one of these, you got to have how many of these? 2. So there's actually a pretty big salt. Okay, the whole thing. What's the difference? One's neutral, one's ionic. It's the only difference. Now, it used to be, back a while, there was a huge difference in cost. Because this was original, and then they came out with Nexium, and so they could charge you more. When that one went off patent. But guess what, guys? When this goes into the stomach, what happens to it? The stomach is full of what?
Acid.
H plus. And if you react that, that's a strong base. You react with H plus, what's it going to do? It's going to protonate, and you got this. So you spend a lot of money, so when it goes in your stomach, it's this. Okay? Now, they probably got a new patent because they said this probably dissolves faster in the stomach. Why would it dissolve faster in the stomach? Because the stomach is water, not acetone. And this is more soluble water? What?
Polar.
What? Because it's ionic. So it may dissolve faster, but as soon as it dissolves, guess what? It's this. Y'all think about it. Last thing, well, we got it. On the back, it's, this is a little, here's the colored version. Solubility, molecule at the top. With R groups on the nitrogen. What's an R? I don't see it up there. I see ruthenium and rhodium, but I see no R. What's an R? Some type of carbon group. It's got to be defined somewhere else. R is defined down here. Solubility between water and cyclohexane. These don't mix, they form 2 layers. You can have the compound in here though. If it's methyl, if the two methyls on the nitrogen, the compound actually prefers water over cyclohexane. That's already an exception because it's a neutral organic molecule. We think it might prefer the neutral organic solvent. The problem with cyclohexane, it's so nonpolar. If we were doing this with something like diethyl ether or ethyl acetate, then it would probably prefer those. Then the demo wouldn't be as good because, well, you wouldn't get any differentiation. Okay, let's see what we're trying to illustrate here. Both methyls, it prefers water. If we make them both ethyls, it's starting to prefer the cyclohexane. There's a little bit of yellow still in the water. This is after it's being shaken up, allowed to separate. So it tells you that you do have some still soluble down here. You make these propyl groups, methyl propyl. Everybody have watched the video, nomenclature video? Now even more prefers the cyclohexane. Does this trend make sense? What are we increasing as we come to the right? Are we making the compound more polar or less polar? Less polar. As we make these groups bigger, these nonpolar groups bigger, we're making the whole molecule less polar, and so it prefers or it starts hating water. These are hydrophobic groups. These are going to hate water. This is, I think, a good illustration. And it starts liking the organic solvent more with these organic hydrophobic portions. And that's it for that. Acid-base chemistry. By the way, that compound is with the methyls. They're all called methyl red, propyl red. When they're solids, they're red. When you dissolve them, they're yellow. So the red comes from the solid, the color when they're solids. While I got that structure, I know you may be put it away, don't worry about getting it back out. Nice structure there. Very conjugated. What do I mean by very conjugated? I'm referring to what? More than just lone pairs, but what am I referring to as conjugated? Again. Lone pairs and p orbitals, but more than just lone pairs. So there can be other p orbitals without lone pairs. Conjugation refers to p orbitals lined up, like toy soldiers. P orbital, p orbital, p orbital, p orbital, boom, 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 all the way through, p orbitals, right? How many total p orbitals present? How many electrons in p orbitals? Which would be called pi electrons. Electrons that are in p orbitals are called pi electrons. How many pi electrons does that molecule contain? Those are examples of some questions, right? You need to understand structure. Hybridization. And there were questions like that in the workbook. Number of p orbitals, number of pi electrons, things like that, yeah? Very conjugated structure. And the high degree of conjugation is what leads to the color. We'll talk more about that when we get to UV vis. Acid-base chemistry. Okay, there's some good warm-up questions there. Very important question here. One that you guys typically have trouble with. I'm not sure why though. Standard acid-base reaction. You guys did acid-base in June? Okay. Standard acid-base reaction. Hopefully no different than Zinkin. The standard acid-base. Hopefully this looks like review. The acid-base mechanism. How do you show an acid-base reaction? How do you predict outcomes of acid-base reactions? When you have an acid or base, you're going to have a base and an acid. You've got to identify those. The basic atom, typically a lone pair, is the business end of the base, right? What does the lone pair do? The lone pair reacts with the proton on the acid. Proton meaning the hydrogen, right? This is your arrow mechanism. These electrons, okay? And also now we'll circle the electrons. These electrons go make bond to H. The two electrons that are between the rest of the molecule and the hydrogen that's being abstracted, these two electrons move on to the rest of the molecule. Here I just call it Z. And when we do a mechanism, we're showing arrows. To show what's going on, to show the electron movement. What does the arrows mean? This is now bonded to the H, and that's right here. The basic atom is now bonded to the H. That's two electrons, right? Covalent bond, two electrons. Those two electrons used to be what over here? A lone pair. The lone pair is now a bonding pair to the H. This bonding pair did what? It moved onto the Z as what? As a lone pair. So it went from being a bonding pair to a lone pair. The arrows have to mean something for you.
Should the Z have a charge, or is that lone pair kind of representing the charge?
Do I not say that charges were not shown? Yeah. I either did not say it or I should tell you here. No, I'm not showing charges anywhere. Yeah, very important. You often will have charges in an acid base. I didn't put them there because it could be either. This could be charged and thus that would thus be neutral, or that's neutral and thus this could be charged. What is consistent is bonding, now lone pair. And guess what? The previous page with the acid base, you do it the same way. Any Bronsted-Lowry acid base reaction right there. Right? Hopefully you talked about this in Gen Chem and you were able to do any acid base reaction. Recognizing acids, recognizing bases. Okay, I explained the two arrows. There you go. Charges at the bottom. I discussed it. Yeah. Okay. Now you can go back and you can do the same thing right there. We will look at that at some point and see if you have any questions. Okay. Acid-base chemistry. Let's get into it. A lot of this first page is sort of review. I'll just tell you what I'm telling you here, just a standard acid-base. Showing just an acid here. This is a generic ionization. Okay? There's really no base here in this example. To do any acid-base, you've got to have both an acid and a base. But you also just see an acid ionizing, and that's really just half of your mechanism. That is, these two electrons are just moving on to the A. Here I called it A, in the previous example I called it Z. Well, guess what? Your textbook may use A, your textbook may use Z. What does this arrow mean to you? These two electrons are moving on to A as that. Now here I did show charge. If this is neutral, you generate H plus and the rest becomes minus. The atom that the H was bonded to becomes minus. Now this is an equilibrium, right? Ka described by this over this. Stronger acid will have a higher Ka. Based on that equation. Here I'm just showing you water now. Water coming in as the base. So now we have a base and an acid. And our good old acid-base mechanism, these electrons take the H, those move on to A. This is condensed, but now it used to be a lone pair, but now it's bonded to H. And we have A minus. We have charges. pKa equals negative log of Ka, thus stronger acid will have a lower pKa. All of this is just basically review. Let's get on down here. Examples of acid, ACl has a pKa of about -7. Again, based on that statement, lower pKa equals stronger acid, stronger acid. Acetic acid. What functional group is this? Carboxylic acid. Are acidic. We call it carboxylic acid. But they're weakly acidic. pKa of about 4. Weak acid. Which means it's only partial ionization if you put it in water. Where a strong acid is completely ionized, right? Alcohols. Not as acidic as carboxylic acids. pKa of about 16. We saw the difference in the extraction example. Much less acidic. They're considered neutral, but they can act as acids. Anything with an H theoretically can act as an acid. Water can act as an acid. Do you call water acidic? No. That doesn't mean it can't act as an acid. Typically, you don't call something an acid until the pKa gets below blood pH, which is about 7, right? Then you start calling it an acid. That's just historical. Alkane, CH, not that acidic. pKa of greater than 40, nearly never acidic. Of course, you call it neutral. Okay, how do you rank these? You just memorize such? No, you got to be able to get a feel for ranking because there's numerous other functional groups that you might be asked to rank. How would you rank them? The degree of acidity is based on, I think, 4 things. Wasn't solubility also that type IMF was 4? Oh, okay. We got 4 here as well. Number 1, we'll do each of these. Number 1, electronegativity and size of the A. When A is an atom, okay? This is the atom that the proton at the top was bonded to originally. Let's look at the electronegativity and the size. How does that affect things? Electronegativity. Consider these two. Water versus HF. Which is more acidic?
HF.
It should probably be easy because HF is analogous to ACl. Okay. Yes, HF is more acidic. But why? Let's approach this systematically. What do we need to look at? What you really need to look at is not these two. You need to look at where they're going. When they act as acids, okay? What do the conjugate bases look like? F minus or OH minus. This is what you need to look at. And you need to say which is more stable. F minus is more stable than OH minus. Why? Because F minus is more electronegative. F is more electronegative than O. What does that mean? F can handle the negative charge better than oxygen can. It likes negative charges more. F minus is more stable. Since F minus is more stable, HF is more acidic. Why? Because we're saying which one's going to come, okay, which one's going to go here more? HF, because F minus is saying, hey, I want to be formed. I like being formed. The oxygen is like, hold on. Don't like being at minus as much. So it's not as eager to come over here. It's not as eager to act as an acid. So let's look at the stability of the conjugate base. Water versus NH3, which is a stronger acid. Well, what do we need to look at? Conjugate bases. What are the conjugate bases? Are they shown? I don't think they're shown. When water gives up the proton, now I'm thinking only half of you could actually show that right there. Now maybe for water you could, but what if I changed it up? You need to go back and look at your reaction. This is the conjugate base. When this gives up the proton, that's what's left. That's the conjugate base, correct? When water gives up a proton, it forms this. When ammonia gives up a proton, it forms what? You do not need to just pull these out of the air once we get more involved examples. Do your acid-base mechanism, just like the previous 2 or 3 examples. What you're left with after the reaction is the conjugate base. Which one's more stable? This has got what, 3 lone pairs? Which is more stable?
OH.
Hydroxide, what? More electronegative. I don't mind being as minus. The nitrogen is like, hold on, I don't want to be minus relative to what oxygen would say. Water is more willing to come here. Water is more willing to act as an acid. Water is more acidic. Water versus methane. This becomes OH minus. This becomes what?
CH3 minus.
CH3 minus, which is more stable. Oxygen, much more electronegative. Carbon doesn't want to be minus. Hold on. That thing's like, hold on, I don't want to give up an H+. I don't want to act as an acid because I'll have to become minus. And oxygen doesn't mind that. Very unstable. More stable, more acidic. Very rarely are we ever going to see a CH being acidic. We will see some in organic too a little bit. Carbon typically doesn't like being minus. You can form carbanions, but not as easy as you can from, not as easy as forming nitrogen or oxygen anions or halide anions. Okay, size of the atom is also here. So it's 1A and 1B. Which is more acidic, ACl or HBr?
HCl.
What do we need to look at? We really need to look at the conjugate bases. Which is more stable?
HBr, hydrobromic.
Which is more stable?
HCl.
We're not talking about HCl. We're talking about Cl minus or Br minus. Which is more stable?
Br minus.
Why Cl minus?
More electronegative.
It is more electronegative. Iron to the right, electronegative. Chlorine more electronegative. But Br minus is more stable. Is that why you said Br minus? Because you were reading, don't read
Because
ahead.
it's bigger. Take that charge. Spread it out. It's bigger.
We have an exception here. When you're in the same group here, okay, vertical, size trumps electronegativity. Br minus is more stable. Even though Cl minus is more electric, it's bigger. And thus the charge is spread out more. The charge is more diffuse. And that trumps the electronegativity. Only if you're in the same group. Straight up down. Okay? Before we were going across. Where it can become a little hard to determine is when you start going vertical. Okay? HBr is actually more acidic because Br minus is more stable. That is, the HBr is more willing to come here, but it's going to, okay? Which is more acidic, HBr or HI?
HI.
Which is more stable, Br minus or I minus?
I minus.
Actually, I minus, even though it's not as electronegative. Why is it more stable than Br minus? It's bigger. And Size trumps electronegativity when you're going straight up and down. HI is the most acidic of your hydrohalic acids. And I minus is the most stable anion of those. What's the most acidic hydrogen in this compound?
On the alcohol group.
The sulfur.
CH or OH? CH is really acidic because you really want to have a carbanion. Really the question is, where would you most like to make them anion? That's really the question. Well, let's just say, NH or OH?
It's more electromagnetic.
O minus more stable than N minus. Because O minus is more electronegative. So the OH is more acidic than the NH. What about the OH versus the SH? Which is more stable, O minus or S minus? S minus more stable because it's larger. So this is more acidic than that, and that's more acidic than this. And those are more acidic than the CHs. Yeah, that's the most acidic, your SH. Number 2 on the previous page was inductive effects. Inductive effect is a type of electronic effect. Inductive. Look at these 2 examples. This is ethanol, 2-carbon alcohol. Very similar to ethanol, except we added a fluorine out here, which is more acidic. Well, we got to consider the conjugate bases. O minus or O minus? They're the same. That doesn't give you the answer. What's the difference here? One has an F here, and that one has an H. What does the F do? We have polarity here. You've got a CF dipole. The F is pulling. Tug of war. The F is pulling electrons, right? Dipole. We didn't say it before, but when you pull electrons through single bonds, that's called induction. Induction or inductive effects. That name comes from probably the presence of the fluorine pulling induces a dipole. It creates a dipole, but we're calling it inducing or inductive. Through single bonds, though. But this is like tug of war, so that makes that partial minus, partial plus. But it's pulling. The effect is not just here. The effect is sort of all through the molecule. Although it can kind of get weaker as you get away from it. So the F is pulling. What's that going to do to the stability of this O? It's going to make it more stable. Everything would prefer to be more neutral-like. Okay? If you've got a lot of minus here, okay, how can I stabilize you? Pull minus away from you. If you're minus and I push minus towards you, is that going to stabilize you? No, you're going to get even worse. You're going to be like, I got too much minus. You got a lot of minus. Well, let me pull some away. Pretend I'm a fluorine pulling some of that minus away. Now, it doesn't have to be bonded directly again. The effect can be felt all the way through. The fluorine is pulling some of this minus away, making it more towards neutral, more stable. That doesn't have it. In fact, we can actually invoke this. An sp3 carbon is actually electron donating by induction. Now, there's actually no dipole here in our previous discussion. So this is just sort of a statement. An sp3 carbon donates by induction. The reason is called hyperconjugation. It's a little sophisticated. We won't really get in it right now. It's a statement we're making. Fluorine withdrawing more stable, thus which is more acidic. It's more acidic. More acidic. Which is more acidic, methanol or ethanol? We can just, if you allow me to shorthand, we can consider the anions. Which is more stable? What's the difference? An extra sp3 carbon? What does an sp3 carbon do inductively? It donates. So if you got a minus here, and you got an extra donation, is that going to stabilize that? No. That one's more stable then. Because this one is destabilized by induction. How do you stabilize a minus? You pull electrons away. See if you can get this one. All right? We're testing. What if it was a positive? How would you stabilize a positive? You would not pull electrons away. That wouldn't have, you would give an electron. You would push electrons towards. Right? I mean, it's the opposite. All right. But right now we're dealing with anions. You pull electrons away. Which is more acidic, ethanol, or this is actually called terbutanol. It's 4 carbons, but it's a tertiary carbon. It's called tertiary butanol or terbutanol. Which is more acidic? Not that one. This one. Why? Okay, we did one chain here. These alkyl groups all donate. When you have branching, it's like there's 3 different donation tunnels or incoming lines or whatever. This one here really only has 1. We're considering the anion, right? When you look at induction by carbon, this branching is like triple the amount. That's how you have to look at it. Even if this was this long, this would only be a 1. The branching, it acts like 3, and so it's simplistically stated, it could be like 3 different levels of donation. Is that going to stabilize the minus? You're a minus, and we got 3 people just pumping electrons in. That's bad. It's not going to stabilize you. By default, this one is more stable. That one's worse off. This one's more likely to become minus. Think about these here. Please think about those. And then be looking forward. Okay? Please be looking forward. Resonance. Hybridization. Structure. We're going to start building upon that.